The Hubble Deep Field is one of the most iconic images in all of astronomy. It's this time when they spent thousands of hours with the Hubble Space Telescope staring at a seemingly empty spot in the universe. And what they saw were tens of thousands of galaxies out to the very limits of what Hubble could see. And of course, it's natural to wonder, when is the James Webb Space Telescope going to do its version of the Hubble Deep Field? It is so much faster, so much more powerful than anything Hubble can do. And already the initial tests that astronomers have been doing have shown just what is capable with a fraction of the time. A James Webb Space Telescope Deep Field is kind of inevitable. So my guest today is Dr. Viraj Pandya. He worked on the various flavors of the Hubble Deep Field, has been working on a lot of really interesting galactic surveys using James Webb, examining galaxies. He's on one hand done some really interesting research into the shapes of galaxies seen in the early universe. They're not what you'd think, not the grand spirals or giant elliptical galaxies that we see around us today, but they were more like tubes, as he calls them, breadsticks. And this was surprising and is sort of a really interesting field of study so far. We spend about half of the interview just talking about what he has discovered with James Webb so far. And then we shift gears and talk about what does the future hold for giant surveys? When will we get that deep field? And I think you'll find that part of the conversation as well really fascinating and get you pretty excited about what the future holds. All right, here's my interview with Dr. Viraj Pandya. Viraj, if you were to sort of describe the typical galaxy in our neighborhood, what would we see?
That's a great question, Fraser. So the typical galaxy in our neighborhood, it's a spiral galaxy. So I have this analogy that I make inspired by working in New York City, where if you think of galaxies as coming in terms of three different dominant shapes, you can think of elliptical galaxies that are intrinsically round in 3D. So these are like balls of dough that are perfectly round. And then you take that ball of dough and you flatten it along one axis, and you get the greatest thing in the universe. You get a pizza. And so the pizzas are what dominate in the local universe. And sometimes you can have pizzas with like balls of dough in the middle that we call bulges. These are the most common. And as you go to like the most massive nearby galaxies, they start to preferentially become like balls of dough, just like pure roundish 3D balls of stars.
And those, I mean, I really do like that pizza analogy. I may borrow that. But this idea, I mean, when we think about the Milky Way, I mean, we're not just this flattened disk. We are surrounded by this cloud of satellite galaxies, many that we have ingested. So if you sort of look closer at the various types, when you see the spirals, when you see the ellipticals, do they have similar kinds of clouds of satellite galaxies around them as well?
Yeah, the Milky Way, our own galaxy, which is, it's like a spiral with a small bulge in the center and a bar, and of course these spiral arms. But it's also surrounded by this swarm of like 60 little satellite galaxies. Most of them we say are red and dead, in the sense that most of them don't have any interstellar gas, the fuel for forming new stars. There's a handful, like the Large and Small Magellanic Clouds, which are two of the biggest satellites of the Milky Way, that do have gas. They're forming new stars. And then if you look at other nearby galaxies like Andromeda or giant ellipticals, they also have their own satellite populations that are orbiting, as exactly you said, like in a halo. And that halo, is made of is predominantly, we think, made of dark matter. And we don't know exactly what dark matter is, but we can infer its presence because it affects the motions of the stars in galaxies.
I actually didn't know about that idea that the satellite galaxies of the Milky Way are red and dead, that they used up their reserves of gas and dust for star formation before they got sucked into the larger galaxy. And so it's when we look at the structure of the Milky Way, thanks to, say, observations by Gaia, we see the streams of torn up satellite galaxies that joined us in the past. And so those ones, I'm assuming, did bring their gas and dust into the galaxy.
Yeah. So there's definitely like these two regimes. So these like streams of stars, like kind of strewn out, like the Magellanic Stream. These are the remnants of galaxies, satellite galaxies that couldn't survive, and they've been literally torn apart because of the immense gravitational pull of the Milky Way's halo. But there's about 60 galaxies that are still like bound collections of stars, but they don't have. Most of them don't have any gas to form new stars, except for the LMC and
Right.
the SMC. Yeah.
Huh. That's really interesting. Okay.
Yeah.
Sorry, I just rabbit holed there for a second, filled in
Yeah.
gap in my knowledge. So then as we expand our view out to, beyond the local group, looking at, say, the Virgo supercluster, galaxies that are in the tens of millions to hundreds of millions of light years away, does this story change, or do we just see kind of the same thing nearby?
Yeah. So as you go towards like nearby clusters of galaxies, which are like the New York cities of the universe, where all the galaxies kind of hang out, something does change in the sense that as you go to groups and clusters of galaxies, you start to see many, many more red and dead galaxies, and also many more elliptical type galaxies. So it's kind of mind blowing for me to think about it this way. But the Milky Way right now, okay, we're in this local group. We have the Andromeda, another nearby massive galaxy. We have the Triangulum galaxy, and then we have this smattering of satellites around the Milky Way, around the Andromeda galaxy, and Triangulum, and then scattered throughout the local group. But if you go to, say, the Virgo cluster or the Coma cluster, the satellites in the Coma cluster and the Virgo cluster, many of them you can think of as like Milky Ways. So imagine like a Milky Way mass galaxy being a satellite around a factor of 10 to 100 times more massive galaxy or halo.
And so it's like one stage larger structure than what we have around the Milky Way. It's like, I don't know, like
Exactly.
Moons are to planets are to suns, and then in this case, spiral galaxies are to giant galaxy clusters.
Exactly. Yeah. And there's a long-standing puzzle that when you go to these like large clusters of galaxies, a lot of the 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 inhabitants, the galaxies in these clusters, they don't form stars at the rate at which they would if they were not in the cluster. Like the Milky Way today, it's not great at forming stars. It's kind of average. We call it a green valley galaxy, as opposed to like a blue star forming one or a red and dead elliptical. But if you put the Milky Way in a cluster like Coma, it would be forming. It would not be forming stars. Its gas would probably get stripped and
right. And so clearly there's this cycle going on at various scales. We see it in the dwarf galaxies that are around the Milky Way, and then you see the same thing, but just at the next level up with their interactions in these larger galaxy clusters. Okay, so as we look farther out, then say we bring the Hubble Space Telescope online, and we start to look out to the very limits of where Hubble can perceive galaxy structure. What do we see? And I guess how far away is that, and how far back in time is that?
Yeah. So Hubble, in principle, it was able to observe galaxies back to a few hundred million years after the Big Bang, but its sensitivity wasn't as great as, of course, now the James Webb Space Telescope. But even with its, despite that, it revolutionized our understanding of galaxy formation. And one of the things I like to point people to, which is kind of forgotten these days, I think, is in the mid 90s, when people started to, create some of the first like proto Hubble Deep Fields, they found that when they pointed at, a relatively empty area, patch of the sky, smaller than the full moon, they found that as you look at distant galaxies that existed maybe 10 billion years ago, and this includes galaxies that we think had the masses and star formation rates of like what we think the ancestor of our own Milky Way was. So a lot of these Milky Way progenitors that existed 10 billion years ago Hubble found in the mid 90s and early 2000s, they were very linear looking. And as you started to approach the detection limit of the Hubble imaging at the time, you started to get dominated by these very linear looking structures, galactic structures. And there were lots and lots of proposed explanations for this. One is maybe Hubble is just not sensitive to detect like the rounder looking thing. So if you imagine you have a spiral galaxy like the Milky Way, right? So you can see it from a variety of viewing angles, right? And it turns out that if you look at a Milky Way like a spiral galaxy edge on, then it's going to appear brighter, so you're more likely to pick it up in your observations. But if you take this like thin disk, this thin Milky Way spiral type thing, and you put it face on, then the light is more diffuse and it actually has a lower what we call surface brightness, and so it's very likely that you won't pick it up in your imaging. So this was one idea back then, that maybe we're seeing all of these elongated linear structures just because there's like a bias against detecting the face-on ones.
And this is actually a really big problem in astronomy. I mean, we experience this when you walk outside and you look up at the night sky. You're seeing all these stars, and all of them are weirdos, right?
Yeah.
There are almost no stars that you can see with your eyes outside, except for a couple of close ones, Alpha Centauri, things like that are just the same kind of brightness as the sun, and definitely not the most common stars like the red dwarfs. What you see are stars with many times the mass of the sun, stars that are hundreds of light years away. Each one of them is a bizarre, rare, very bright thing. And so if you think as you look up in the sky and like that's normal, it's not normal. Like there's all these hidden stars that you don't see just because they're so bright. And I know that this problem comes up a lot with, it's like almost like survivorship. You guys you sometimes have a term for this, right? But it's like survivorship bias. Like when you look in the field,
That's right.
You're seeing a bunch of stuff. It's biased towards the kinds of stuff that can be seen, and that can totally skew your results.
Yeah, exactly. So we call this a selection effect, or in this particular case, surface brightness detection bias.
Yes.
Like what actually makes it into your sample of observed galaxies. And I mean, there are ways to quantify this. So, a lot of, I think, it's pretty standard. Like I've done this for my recent JWST paper, and, people have been doing this for as long as people have been studying galaxies. You can take the typical characteristics of your image, or just take your image itself, the images you've taken with your telescope, and you can inject fake galaxies into those images. And their properties, where they are. You can assign them various different colors and orientations and brightnesses, and you can then run that kind of mock image through some detection pipeline to detect sources, to detect galaxies, and then once you do that, you actually walk away with a better understanding of like, okay, here is the limits of my data, the detection limits of my data. And if I'm trying to draw conclusions about galaxies that are fainter than that limit, I should be very careful, because I don't, I have severe biases maybe.
Huh. And I mean, it feels like that should almost be like your instinct. When you're running up against the edge of what your telescope can do, you should assume by default that there are all kinds of selection biases going on there.
Yeah, that's exactly right.
Yeah, that's interesting. All right. So you got this hint that there were these strange linear shaped galaxies were starting to appear more often the farther you looked back in time.
Yeah.
JWST comes online. Now you're able to see even farther, even deeper. What do you see?
Yeah. So I worked with an amazing team of astronomers, 100 people and more actually. This is a collaboration. It's an early release science collaboration for the James Webb Space Telescope, known as SEERS, the Cosmic Evolution Early Release Science Survey. Steve Finkelstein is the PI, one of my former mentors as well. So we saw all these papers coming out in the first 2 years from JWST, which were convincingly showing that there were cases where Hubble had completely missed disk galaxies. Like they just weren't even, they were just noisy images from Hubble. You couldn't make anything out. But then JWST imaging of the same patch of sky reveals all of these nice disks, including many face-on ones. And so there were a lot of papers about this and claiming that uh, the fraction of galaxies that are classified as disks in Hubble imaging drops dramatically as you look further and further uh, to larger distances. But then the fraction of disk galaxies, according to James Webb imaging, it was at like the 40 to 50% level. So where it was like less than maybe a percent or 10% in Hubble imaging, it was the disk fraction was 40 to 50%. So I got very excited because I thought, okay, well JWST has solved this puzzle where maybe it's detected all of these round face-on disks that Hubble had missed, and we don't have a crisis. Maybe there's no puzzle anymore to explain these linear things, this overabundance of linear galactic structures. So I actually went in with the Sears team and we actually characterized the essentially the distribution of the projected ellipticities of all galaxies in the Sears JWST imaging. So what that means is you have galaxies on the sky, 2D sky, they're projected, and you can essentially fit every galaxy with some kind of ellipse, right? And then you can characterize every galaxy by the ratio of the short axis to the long axis of its best fitting ellipse. That's called the projected axis ratio. And then for galaxies that are like at a similar distance from us and that have a similar mass or brightness, we can just do a simple counting exercise. We can just look at the distribution of that projected axis ratio, projected ellipticity. And if you, sorry, go ahead. Yeah.
No, well, I was just going to ask. So, like, if you, like, you have done enough calculations for different kinds of galaxies, so that when you see a certain shape in the sky, you're able to calculate what its orientation is compared to us as the observer, and then you can do that at scale. Like, you can see a whole bunch of galaxies in a field. Your computer algorithm can run through them all and go, this one's pointing this way, that one's pointing that way, this one, and so on, and be able to sort of do a giant survey quickly.
Yeah, exactly. And it, this is a statistical exercise. I can say some more later about ways to follow this up to get smoking gun measurements, constraints on the orientations of individual galaxies. But when we measure the projected orientations, the projected shapes of these galaxies, we have certain expectations. So, if we think that the universe is isotropic in terms of, galaxies being randomly distributed throughout it and randomly oriented, and in our standard picture, right? If we think galaxies start out as spirals, as disks, then you should see disks from many different values. And so you actually end up expecting a roughly uniform distribution of galaxies with different axis ratios. You should see equal numbers of round ones and equal numbers of edge-on ones, like thin lines. And we don't see that. Even with JWST, we don't see a uniform distribution. Instead, the distribution is very asymmetric, and it's skewed heavily in favor of still like these elongated, linear-looking galaxies, even with the improved sensitivity of JWST. And that's telling us that these early galaxies, like the ancestors of the Milky Way that existed 10 billion years ago, they cannot all be like spiral galaxies, like pizzas. And they also can't be balls of dough, which would preferentially show up actually looking round. No matter what you look at a ball of dough, it's going to look round in projection. So there's actually another possibility that my co-authors and I are advocating for. And this is to complete the New York City, baked product analogy, right? We have dough balls, you have pizzas. Now take the pizzas and flatten them along one of the other two axes, and you get my other favorite thing in the entire universe. You get a breadstick.
Right. Okay.
So breadstick is like this third class of types. It's called an ellipsoid, a prolate ellipsoid shape. And we think that we're seeing lots and lots of galaxies at early times that maybe in 3D are shaped like breadsticks. They're not like nice circular disks. They're heavily flattened along a second axis.
And so
And
what
yeah,
when so if we could fly close to one of these things and take a look at it,
yeah,
like if we were like Andromeda close,
yeah.
what would we see?
That's a great question. So yeah, you can do a little thought experiment. If you fly up to one of these breadstick or cigar shaped galaxies in the early universe, we think what you would see is lots and lots of other little galaxies, maybe undergoing kind of they're on very radial orbits, so they're kind of undergoing um, in the process of undergoing mergers, essentially along a preferential direction. So our standard thinking right now for why these galaxies are shaped like breadsticks is they are embedded in dark matter halos, right? Like we talked about for the Milky Way. But the dark matter halos of these early galaxies, they're not like the relatively roundish dark matter halos of the Milky Way today. We think the dark matter halos of these early galaxies that are breadstick shaped are also elongated. So the dark matter halos are also like scaled up versions of like a breadstick shaped ellipsoid. And that dark matter halo's longest axis is oriented in the same direction as the long axis of the stars. And finally, this entire system we think is embedded in a dark matter cosmic Webb filament. So you talked about, we talked about clusters of galaxies before, right? And so these are found at like the intersections of cosmic Webb filaments. Uh, and filaments are, where we think like the characteristic typical galaxy, like the Milky Way progenitors, like where typical galaxies form. They form in filaments and they make their way towards these clusters over cosmological timescales.
And so
Um,
back to that idea, if I was looking at the galaxy Andromeda distance away, I wouldn't see like a two-armed, I don't know, galaxy that would, had a central bulge and then one arm leading forward, in a straight line. I would see like this giant collection of dwarf galaxies that are all together in a line, merging and star forming and beginning the process of coalescing together, which is different from what you would have originally expected, that it would be like they'd be coming together in a kind of spinning disc, but you're seeing, in
yeah,
fact, it's like this weird line, and that matches the larger scale structure of the universe, cosmic web, the sort of the amount, the distribution of dark matter that's believed to be out there.
yeah, that's right. And
That's interesting.
another really cool thing about this, I wrote a paper about this in 2019, and it's how I first became aware of this particular area, of galaxy formation. So my advisors at the time, Joel Premack, Sandy Faber, David Koo, and Avishai Deckel, we had this idea that if these linear looking early galaxies were in fact what I'm saying, that they're like these collections of little, galaxies undergoing mergers along a preferential direction, and they're embedded in these dark matter filaments. Well, something else you might expect to see is actually these linear looking breadstick shaped galaxies may actually point towards one another in 3D, if they're forming along, if there's like multiple of these breadsticks forming along filaments. And so if you take yourself back to Earth and you look at the 2D projected sky, we expect that maybe in projection, these early galaxies on the sky are not going to be randomly oriented. They're going to maybe point towards one another on average. And this is something that we'll be able to get a handle on and directly map out with the upcoming Roman Space Telescope in a few years.
Right. So in other words, if these lines are the progenitors of the larger spiral galaxies, then the next step that you should see is these streams of stars crashing into each other and then actually beginning that star formation, beginning that larger spiral galaxy formation. And I
Yeah,
guess the
exactly.
the ones that are kind of trailing behind, that are going through their star formation, they end up as those satellites that don't get fully consumed by the spiral.
Yeah, that's right. We don't know exactly how one of these breadstick shaped things will turn into a spiral like the Milky Way. There's, we do have very high resolution simulations of the universe, of individual galaxies like the Milky Way and their evolution, over billions of years of cosmic time. And these simulations, by, for example, Daniel Severino and Joel Primack and Avishai Deckel and others, they do suggest um, that there's some process. In the beginning, these galaxies are shaped like breadsticks, and then they continuously undergo mergers and they form stars in their centers. So over time, you get a increase in the central mass density of stars. And during the breadstick phase, stars can actually pass arbitrarily through the center of the galaxy, which is in contrast to like a Milky Way spiral, right, where the stars are on circular orbits. They don't generally go through the center. They kind of just stay on circular orbits. But in these breadsticks, you have a growing mass density at the center of the distribution because you have mergers. Maybe you have cold flows of gas towards the center that form stars. And so these stars that are on initially kind of radial orbits through the long axis through the center of the system, they might start to get deflected. They may start to get deflected off of their original orbits because of the central mass density collection of stars that's growing, and the entire system may kind of puff up. And how exactly that process then leads to the formation of a disk or a central bulge is not well understood at all. It's very complicated and maybe chaotic.
Well, I think of an analogy with like the Lagrange points. Like think about the L4, L5 Lagrange points, which lead and trail the sun in the solar system. And you get this very chaotic system of these objects orbiting around inside of it. But the way the torques work, if one of these objects starts to drift out or has a three-body interaction and drifts outside of where it is, it experiences a torque that pushes it back into the region and creates this sort of giant fluffy mass that is perfectly related to the gravity of both the sun and the earth, but they're also trapped there. And so you can sort of imagine that as these things are trying to escape, the larger dark matter strand is sort of keeping things constrained. It's very bizarre. I mean, I think as you think about the shape of the stars, you must just spend a lot of time thinking about that invisible, larger scale dark matter structure. If that's driving it, then you're seeing its echo, its reflection, its shadow in stars.
Yeah, no, it's really exciting. This is why we want to do a couple follow up studies, and one of them I just mentioned earlier is we want to go in with the Roman Space Telescope in a few years and ask, do we actually see these galaxies tracing out like on huge scales, like these kind of strands, the filaments in projection on the sky at different distances from us? Because that would be a nice kind of almost smoking gun test. No one's ever detected these strong intrinsic alignment signals, as we call them in the field. No one's ever detected them for like these low mass galaxies. We've known for a few decades now that like the most massive, red and dead ellipticals at the centers of clusters actually point towards the ellipticals at the centers of other clusters because they retain their memory of their initial formation. So that's one thing. And then the other thing is we want to try to. It's very challenging to do this, but there's this kind of there's this fundamental issue for individual galaxies. If you see any individual galaxy that looks like a linear structure in projection, no one can say, like from the James Webb imaging alone, is this elongated galaxy in projection? Is it a circular disk in 3D? Is it an oval disk? Is it one of these breadstick shaped or cigar shaped things? The smoking gun way to test that is you actually have to get a spectrum of the starlight of this thing. And that's super challenging because these things are so small, they're so faint, they're so far away. But if you can do that, and if you can detect the absorption lines from the stars in these galaxies, then you can actually tell what kind of orbits the stars are on. So if you have a circular disk seen edge on, you expect the stars to be on circular orbits. So you expect to see a rotation curve. One side will be, moving away from us, and one side will be moving towards us as the stars orbit on circles. But that's literally impossible for, if these galaxies are like highly, breadstick shaped or surfboard shaped is another beach themed analogy I throw in. Because there we expect the stars to be on these highly elliptical radial orbits along the major axis. And so we are starting to think about, ways to constrain this with existing telescopes, like, of course, James Webb, but then also the Keck telescope in Hawaii. But I think we really need the next generation of 30-meter class telescopes, the ELTs, the extremely large telescopes, which will come online. The European one may come online in 2029 before the end of this decade. And then the two, hopefully, fingers crossed, the two US ones, the Giant Magellan Telescope and the 30-meter telescope, will come online in the early 2030s.
So you must have done the calculation, though. You've got a proposal rattling around in your brain that says, I need this many hours on James Webb to measure, to gather the spectra from one of these galaxies to measure the rotation curve, right?
Yeah.
What's that number?
So
how many hours do you need?
So for
I got some spare time on James Webb. You can have it. How much do you need?
Yeah, that would be awesome. It's going to be several hours at least, because I think the real data that I want is there's an instrument on James Webb. It's called the near infrared spectrograph, and it has a mode called the integral field unit mode, where essentially, like, you have a galaxy, and across the face of the galaxy, you can get spectra at many different points along the face of the galaxy, which lets you then, if you can go deep enough and integrate for long enough, then you can get constraints on the orbits of what is the velocity field of the gas in the galaxy, which is an interesting constraint in and of itself. But it's going to be very challenging to get it for the stars. So it's going to be several hours, and we'll only be able to do it for the brightest, biggest ones.
Right. But I mean, several hours, that's fine. That's acceptable. I think approved.
Yes.
You're welcome.
Yeah. I would love some of your time.
Yeah, no problem. All right. So I want to shift gears now and just talk about these large Webb surveys in general. I mean, people are entranced by the idea of the Hubble Deep Field, that you took this telescope, stared at what you thought was an empty piece of space, and upturned tens of thousands of galaxies. So what is the equivalent of that for Webb right now?
Yeah, so I would say, we have several surveys. Sears is one that I've been involved with. There's a couple others that have already been completed or are nearly completed, like JADES and NG Deep, that are going significantly deeper. So they're integrating for even longer than Sears integrated for. These are great, but they're still relatively small areas in the sky. So there's other surveys also that are a little shallower, but they're trying to get, they're trying to cover a somewhat larger portion of the sky. So, for example, Cosmos Webb. And I think what we're going to see, we're going to continue to see more and more of these like super, super deep, the James Webb deep fields. But those are only going to be in a tiny fraction of the sky, just like the Hubble Deep Field, because it's so expensive. And I'm on a few of them, actually. There are proposals every year for getting time. And this is, like, I think, the first year where the astronomers at large put in huge, we call them treasury proposals, because we want to, create this wealth of like data sets that imaging and spectroscopy that will, serve the community for years and years down the line. So these like ultra super deep JWST deep fields that people are planning now, they're going to be able to detect, redshift 15, 20 galaxies that James Webb was designed to do, right? You won't
So,
resolve those galaxies, but
I mean, give me a sense of that. I mean, I know that when Webb first came online, a lot of people were making a lot of claims about the most distant galaxies that they were seeing. And we were seeing numbers like redshift 17, numbers
yeah,
that are like 2 to 300 million years after the Big Bang.
yeah,
And things have settled down. People have calibrated better. And now we know we're more in the 400 million year regime and not in that earlier regime. What kind of time is involved? Like when I think about Webb, and they always talk about or when I think about Hubble, they talked about like how many hours it took and how many orbits and how many, here's the field of view and here's the most distant galaxies that are being seen. So give us a sense, because Webb is so much faster than Hubble was. And
yeah,
so give me a sense of like, if you were to like take the telescope and point it at one spot in the sky, how long would you want to point it at that spot until you started to resolve those redshift 15 plus
yeah,
objects, or
yeah.
detect
So I mean,
them,
just
not resolve them?
yeah. So just to give you a sense of scale, I was a member of one of the largest Hubble Space Telescope collaborations that kind of pooled together resources from the wider community to take up almost 1,000 orbits of Hubble
Wow.
to create. We always talk about the Hubble Deep Field, right? Because that's like the OG. But there's actually five. There's
Yeah.
five deep fields that are in like strongly crowded, non-strongly lensed regions. So there's the Hubble Deep Field North, the Hubble Deep Field South, and then there's the Ultra Deep Survey. There's the Extended Growth Strip, and then there's the Cosmos Field. And each of these, right? If you go into each of these are five different fields on five different parts of the sky. Sears observed the Extended Growth Strip part of this CANDLE survey, the Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey from Hubble. So each of these five fields from Hubble, you're tiling observations, because Hubble has a relatively small field of view, so you're tiling observations to create like a mosaic. And for any individual part of that tile, it's about 2 months of observing time to get to the depths of Hubble.
One
Okay, so
one
tile,
object in the mosaic, one tile in the mosaic is that long.
It's about 50 days or so. Yeah.
Wow.
For some of these. Yeah. So that's about 2 months of observing time for one part of this bigger mosaic from one of the five deep fields from candles. Now, Hubble, like with Sears, right? We went back to one of these deep fields, the Extended Growth Strip, and for any individual part of our mosaic comparable to candles, it wasn't 2 months. It was less than an hour.
Right.
And with less than an hour, we actually see way more substructure than Hubble did, which makes sense. I mean, Hubble is a 2.4 meter, a telescope, and James Webb is a 6.5 meters. So it's a bigger telescope, more light collecting area, improved, detector technology. But that's just mind blowing to me that 50 days versus 50 minutes. And the stuff that we see with James Webb is just way deeper. Now, yeah.
And well, I remember we reported on this, it feels like about a year ago, there was like versions of this, and they were finding many more galaxies that are in the Hubble Deep Field, like just already, like without even trying. It's already vastly surpassed the capabilities of the same regions in the Hubble Deep Field. And these are tests. These are just like, can we do this? Right?
Yeah. Yeah, exactly. Yeah. And so, yeah, I mean, the limiting, going back to the detection limits of your data, right? Like the limiting magnitudes of some of these early JWST surveys are already comparable to, if not deeper than Hubble's. And you can resolve a lot more substructure in some of these galaxies. So, with Hubble or with James Webb, and Sears, which again is not the deepest data that we already have available compared to like JADES or NG Deep. But with Sears, my paper, we did like these detection limit tests, and we showed that we are going at least 100 times fainter with Sears imaging in terms of like characterizing the outskirts of galaxies that are maybe existed 10 billion years ago, compared to Hubble imaging. So,
but if you just you stared with this new capability, how long is a reasonable? No, not even a reasonable. How much is an outrageous amount of resolution to get? I mean, if 50 minutes gave you more than Hubble, what would 10, like there must be a limit. Is 10 hours enough for one piece of the sky? 20 hours? What's the point where you said, okay, we're hitting diminishing returns at this point?
yeah, that's a great question. Yeah, I admit I haven't thought about that too much, but as people are starting to plan this, I think at least trying to be as ambitious as we were with the original Hubble Deep Field, kind of staring at the same patch of sky for maybe several tens of hours straight, uh, to see how many more faint sources we can pick up, aka very high redshift sources. I think that's definitely feasible.
I mean, it's always a balance, right, between depth and width. I mean, you could
Yeah,
point for 1 hour at a time and move your field of view, and you would reach a certain depth and a certain faintness of object, and you would be able to tell a story about the sky that would keep astronomers fed for a decade. But if you
yeah,
then doubled the time, tripled the time, 10 times the time, that would give you less of a field of view, but you would see fainter objects. And I
yeah,
wonder, like, I'm sure at some point someone's going to have to make this call and say, okay, when we do the James Webb Deep Field,
yeah,
we get 2 hours per frame for the mosaic, or we get 10 hours per frame, or we want 100 hours. Like, do you have any
yeah.
sense of where those diminishing returns? Has nobody done a paper on this? Where are the diminishing returns? Because they exist in Hubble. Like, you must be
Yeah,
deeply familiar with where the diminishing returns are for doing these kinds of observations with Hubble. Why
yeah,
does nobody
yeah.
know this for James Webb?
Yeah, I know people are thinking about this. I don't think about the planning of the eventual James Webb Deep Fields myself, but certainly, um, I think not only is there going to be trade offs between like depth versus width of James Webb, just given maybe our existing predictions for how we think the number density of galaxies evolves as a function of redshift or time. There's also like kind of balancing what James Webb's capabilities are currently with when it eventually overlaps with the Roman Space Telescope, because Roman, I think, is going to be the real player in terms of wide field surveys, right? Because a single pointing with the Roman Space Telescope is equivalent to 100 Hubble Deep Fields. It won't go maybe as deep as like James Webb initially, but people are planning large community surveys with Roman, and Roman is going to have near infrared capabilities. It won't be as sensitive as James Webb because it's a smaller telescope, 2.4 meter like Hubble. But I'm sure people are thinking about balancing, upcoming facilities and then the coverage with James Webb.
But yeah, and it feels like that's like you're looking to do do the entire sky with Nancy Grace Roman, and then do one very specific part with, say, Webb, and then compare and say, okay, great. When we see stuff at the very detection limits with Roman, then we know that means that there are these kinds of things in that region, right? Like, it's like your
Yeah,
Rosetta Stone between the two regions. But I just wonder, like, if you just pointed Webb at one spot in the sky for 10 hours, 100 hours, like, are you going to start to hit the
like
epoch of
confusion limit.
reionization?
Oh, I see.
Are you going to get a time when there's just like too much sky glow from dust in the solar system? Like, I wonder what the limit is. Like, what is the limit of Webb?
Interesting. Yeah, that's a really good question. I haven't thought about that, to be honest. Uh, yeah, no, that's a good question.
Okay, well, it's fine.
I
If you don't know
mean,
the answer, it's fine.
yeah,
It's
yeah,
weird.
I
It's
don't,
I'll keep looking because
yeah,
it feels to me like that. I mean, that question was asked with Hubble, and the answer was gravitational lenses.
mm,
Right. That
that's
the
right. Yeah,
way we see deeper with Hubble is we look for natural telescopes. Those let us push to the very limits of what's capable, and we're limited by the best gravitational lenses that we can find and the most interesting objects that are being lensed by those. Like, and a gravitational lens gives you whatever 10,000 times, 30,000 times
yeah,
resolving power that Hubble could do on its own, and so you're not going to be able to do better.
yeah.
But
That's a really
and you
good,
get spectra, and
yeah, yeah,
and the same things. But in theory, the whole point of Webb was that it could do the kinds of things that Hubble can't do
without the
directly
lensing. Yeah,
without the
exactly.
lens. It just sees it. And so I just wonder if you just turn that thing on and let it run at 10 hours,
Yeah,
100 hours, at a certain point you go, you know what, we're not getting any more information out of this picture. Right.
yeah,
We can't. Yeah.
yeah. That's a really good point. I truly I haven't thought about that. Like, what are the limits? Like, just from if you have so much data that you just can't. Yeah, at that point
Yeah.
just becomes like your, yeah.
And it might be
Um,
we won't find out for a while because the telescope is so oversubscribed, right? That there's a million things to look at that are more interesting. You don't really care about what the ultimate limits are. But, I wonder what
yeah,
questions could be answered. Because then there's like, there were originally plans, like, say, the Origins telescope that was going to
yep,
follow on to Webb. And that was going to be an even larger telescope that would take you even further back in time.
yeah. I
It's
was just
now
going to bring
being,
that up. Yeah,
yeah. And it's being mashed into LUVOIR and HabEx, and you're creating this Habitable Worlds Observatory, which is, I
yes,
can't wait for that. But
yeah.
we also lose the gigantic infrared telescope, next generation. So
Yeah, yeah. I actually just gave a talk. So NASA was interested in, what can the Habitable Worlds Observatory do for this kind of science of constraining the 3D shapes of these early, Milky Way ancestor galaxies. And I mean, it's going to be insane. I'm a little bummed that the 2020 Decadal Survey recommended, like, there were two versions of the Habitable Worlds Observatory, which is itself kind of now the best of Habex and LUVOIR, as you said. And LUVOIR in particular, there was like a 15-meter version, and then there's an 8-meter version. And the Decadal said, given the constraints on, like, coming up with the technology, the engineering challenges, and the funding challenges, we can only recommend the 8-meter version. Um, but even with the 8-meter version, you'll get like 100 parsec resolution in galaxies that existed 10 billion years ago. So like Redshift 2, Redshift 3, Milky Way progenitors, you get 100 megaparsec, 100 parsec resolution. Um, and you'll be able to, like, detect individual, like, star forming regions, um, with, like, the level of detail that we expect for some nearby galaxies today. Uh, and so that's going to offer important clues on, like, well, yeah, what is the 3D structure of these early galaxies, and how do stars form? The stars that we see today in the Milky Way that are 10 billion years ago, where were they forming in the Milky Way progenitor, right, at Redshift 2?
And so when people ask me about the when are we going to see the James Webb Deep Field?
Yeah,
I mean, there's Cosmos, there's Sears, there's
yeah,
was it Cosmic Web, there's Jade. So there are a bunch of smaller surveys, but according to you, that there is a group that is starting to think about what does our
yeah,
version of the Hubble Deep Field look like, and
yeah,
it'll get proposed, and then it'll be run, and it'll come out. So we're still a couple of years away from that. Would you say?
yeah. I would say we're at least 2 to 3 years away, because,
Yep.
yeah, this is the first cycle where I've seen, the proposals were due last November. And, I'm part of some of these, and, they're still being evaluated by NASA and the Space Telescope Science Institute. We'll get decisions probably in the next month. And then it will take, a year to schedule the observations. But even these, right, the proposals that were submitted and may get accepted this cycle, these are still, like, individual teams of, okay, 100 astronomers each. But if you kind of go back and think about a survey like Candles on the Hubble Deep Field, on Hubble, right? Like there were originally two big teams of 100 astronomers each. And they actually, they both put in a proposal to do essentially very similar types of science, go extremely deep, 50 days of integration for individual parts of the, mosaic of these 5 deep fields in Hubble. And NASA and the Space Telescope Science Institute actually said, well, you guys should come together and, we'll award you both jointly the time. And that's how we got these 5 Hubble Deep Fields from Candles. And also the frontier fields are another big thing, as you said, which were targeting strongly lensed, parts where you have massive foreground galaxy clusters. And so we may end up seeing something like that in the next 2-3 years, where lots of individual teams want to, observe their favorite field, but, we might need like the community come together and say, well, we'll have one big collaboration and we'll all share the time, and then everyone will benefit from the data. So the data will become immediately public, and we'll also provide, to the community our codes, our models, our properly reduced processed imaging. So then the community, like this move towards open source science, the community can do the science that it wants to do.
Oh, it sounds fascinating. I'm really looking forward to being able to report on that. So, and hopefully, we're just a couple of years away from that. Well, Viraj, thank you so much for taking the time to chat with me today. I really appreciate it. Congrats on the work that you've done so far. And I think, we're still only a couple of years into this whole process with this amazing telescope. So the best is yet to come.
Yes. Thank you so much, Fraser. This was a lot of fun. And I'll look out for your future podcast. Okay. Thanks.
All right.
Yeah.
I hope you enjoyed that interview. I'm going to give you some more thoughts in a second, but first, I'd like to thank our patrons. Thanks to Paul Rohrbach, Abe Kingston, Hey Twyla, Dougie Stewart, Stephen Krasaki, David Richards, Mark Ansis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplad, Modso, George, David Giltonen, Andrew Gross, Jeremy Matter, Josh Schultz, and Jordan Young, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Okay, so stop asking already. We got the answer, which is that we are in the initial stages of the preparation and plans for a proper James Webb Space Telescope deep survey. Now, there are a lot of existing surveys. There's the JADE survey, there's the SEERS survey, there's the Cosmos Webb survey, and each one of those is surveying one tiny part in the sky. And already they are turning out more galaxies in the fields that they're doing than giant swaths of the Hubble Deep Field. And this is just the appetizer for what is yet to come. But right now, all these groups are coming together. There may be multiple surveys in different regions of the sky, maybe one for empty spot, one for a place that has a lot of gravitational lenses, maybe something else interesting, or maybe the groups will be merged together into one super group and then they will apply for time together. But when you think about how Webb was able to do in minutes what took Hubble days, that what we're going to get out of these surveys should be just as iconic and as memorable as what we saw with the Hubble Deep Field. So I am really excited for what the future holds. I had a really fascinating interview with Dr. Adam Rees, who has also been using the James Webb Space Telescope, but to measure the distances to galaxies with more precision and accuracy than anyone has ever done before. So if you want more about James Webb, here's a link to that interview. All right, we'll see you next time.